all the visible suns as well as much of the invisible matter, matter that interacts with sunlight and other properties that we're used to, only account for a very, very small fraction of that galaxy. In other words, there's a lot more gravity that we can detect by looking at all the suns as they orbit the galaxy than what we're capable of seeing. That part of the galaxy that we know is there but isn't visible to us, and we know it's there because of gravity, we call that stuff dark matter. And it turns out somewhere around 80 or 90% of our universe is made up of this invisible stuff called dark matter. And one of the major unknowns and kind of mysteries that we hope to figure out in the next few years is exactly what dark matter is. If you got some time, I'd suggest you go to Google and try to figure and learn more about it. But we'll discuss it more when I get back on Tuesday as well. Okay, so let's try another sample problem. Okay, here's one. Calculate the altitude of a satellite in geosynchronous orbit. Okay, so here we got an interesting picture. I'll try to explain that in a second. First, let's figure out what a geosynchronous orbit is. If you look here, I've got a globe on your left with a whole bunch of satellites orbiting it. And if you look at one of these satellites as it orbits the Earth, notice that the Earth down below is rotating at exactly the same rate as the satellites. So in other words, if you were living on the Earth and looking at, and notice you go around the Earth once every 24 hours, because the Earth goes around its axis once every 24 hours, and you look up at one of these satellites that's orbiting at the same rate of once every 24 hours, from your point of view, that satellite is always directly overhead. It's stationary. I don't know if you've ever noticed this, but if you look at a TV satellite dish, it's always stationary. You know, if your TV satellite was moving with respect to you, your satellite dish would always have to be moving. Fortunately, if we put these satellites exactly in the right place, from our point of view, they seem to be stationary, and then our satellite dish can just always point straight at it. So for communications, satellites, these geosynchronous satellite orbits are incredibly important. And our job is to try to calculate the altitude of a satellite in geosynchronous orbit. Okay, let's try to do this. So let's go back to the journal here. First thing we do whenever we try to solve a problem is we draw a picture. We know, let's try doing a top view of the Earth. By top view, I mean that you're hovering over the North Pole of the Earth. So here's the Earth, here's the North Pole, and a satellite is going to orbit the planet. And if it's a geosynchronous satellite, then the period of the orbit has to equal 24 hours. We are asked in this question, let's see, what are we asked? We are asked to find the altitude of the satellite. Let's try finding the radius of the satellite from the center of the Earth. Remember, the Earth itself has a radius. Let's call that big R, maybe. And we can look big R up. And, okay, maybe that's all we know for now. So we've got our picture. The next step is to try to draw a free body diagram of what's going on. Sorry, I'm not doing a good job of fitting this all into one screen, but let's keep going with it. Make sure you've got this written down. We're going to draw a free body diagram of the satellite. So here's the satellite. The satellite is being pulled towards the Earth due to the gravity from the Earth. So this is the force of gravity acting on the satellite. Of course, we're going to have a coordinate system because we always do that. And that, again, because it's going in a circle, has to add up to equal mv squared over r, which is the centripetal force. So, this is a free body diagram that looks kind of exactly like what we did before. This is the free body diagram of the satellite. Let's try to see how this one's going to be different. So as we begin to derive equations, which is step 3, we find out that gmm once over r squared is again going to equal mv squared over r, where the little m is the mass of the satellite. The little m's are going to cancel out, and what the problem's asking us to solve for is for, let's go back to the picture, we're asked to try to find this little r right here. So let's try solving this problem for r. Hopefully you're not getting dizzy. First of all, notice that there's going to be some r's that cancel out there. There's going to be another r popping up in a second. We'll get there. Let's solve for little r. When we solve for little r, we get g big M over v squared. G is a fundamental constant of the universe. We know what that is. The big M is the mass of the Earth. We can look that one up because we've solved for it earlier. And that velocity, well, I don't know what speed the geosynchronous orbit's going at, geosynchronous satellite's going at. Let's see if we can figure that out. Remember that the satellite is orbiting with a speed v, so I'm going to go put that back on my picture. We don't know what v is. We're going to try to find out. And remember that v is always equal to distance over time. And the distance in a circle is 2 pi r, and it goes in a circle once every period. So in other words, our speed is going to be 2 pi r over the period of orbit. Okay, let's stick that back down into our equation. What we end up getting is that r is going to equal gm over 2 pi r over period, all squared. That implies that, let's do a little bit of simplification here, r is going to equal gm over period squared, 4 pi squared r squared. Okay, we were asked to solve for r, so when we move that r squared over to the other side, we're getting r cubed is equal to gm period squared over 4 pi squared, or in other words, we get that r, the distance from the center of Earth to the satellite, is going to equal gm period squared over 4 pi squared, all the cube root of. Okay, the next step is you would plug and chug a number into that and see what you get. And let's see if we can do that. Okay, if I've done my math right, and again, always check that, I get that the distance that the satellite orbits from the center of the Earth is roughly 4.2 times 10 to the 7 meters. Let's go back to the question real quick. Again, we're asked to calculate the altitude of the satellite in geosynchronous orbit. So truly, to do this correctly, what we have just discovered is the distance from here to here, and to get the altitude you'd want to subtract out the radius of the Earth. And I'll let you do that part at home. But what you want to notice here, which is kind of interesting, notice that there is only one altitude, one distance from the center of the Earth, where a satellite is in geosynchronous orbit. And when we look at this picture I first showed, notice that this picture here is a picture from the NASA website. You can go look it up yourself. It's pretty cool. Of the position of, roughly 2,000 satellites. And notice as we look at the distribution of the satellites, there is this ring right here. These are all the geosynchronous satellites that orbit the Earth. These are all the things that your satellite TV dishes are pointed at to go get a signal. And of course there's other communication satellites and other things in there as well. And notice that what prime real estate this calculated geosynchronous orbital radius is. People like to put satellites there because that's where we put them to communicate. That's kind of neat. You can actually see it right there in this image of the distribution of satellites. In Turkey, I don't know if you've ever seen the Turkish flag. It's a red flag with a crescent moon and a star in it. Turkey has actually launched a geosynchronous satellite for communication, but they put reflectors on it so it is the brightest thing in the night sky. It's almost like a spotlight looking down at you. And about once a month, the crescent moon is exactly in the right place with this geosynchronous satellite to exactly mimic the Turkish flag. I've got a good picture of this, which I can't find. I'll try to get it later. Extra credit. If you create a VPython program that clearly demonstrates a satellite in geosynchronous orbit around a sphere that's clearly the Earth, you can get some extra credit from that, which we talked about in lab. Okay, I'm going to pause this here and broadcast this one to YouTube. There'll be another YouTube video for today as well that has another sample problem or two in it. So this will stop, and we'll start up the next one immediately after it, if all goes well. Thanks for being willing to work with me on this. See you in a second.